Okay, well, look, I'm very pleased today to have the opportunity to talk with Dr. Grant Ballantyne, who's Director of Technical Solutions with CEEC. Now, Grant's a passionate mineral processing engineer who enjoys implementing process improvements across industry, and he's just recently been awarded the CEEC Medal for 2020 for technical research. So Grant's got over 10 years mineral processing experience in design, optimisation, operation, research and development. With a degree in metallurgical and chemical engineering and completing a PhD at the JKMRC in 2012, and has been involved in successful site-based industry research in 5 continents and 8 commodities. Now, Grant has now moved to CEEC, the engineering company, where he coordinates the comminution group, which includes new technologies and flow sheets, and they're the sorts of things we'd like to talk about today. Also with input at the front end, engineering design and operations, and how to apply enhanced processing technologies such as coarse particle flotation and bulk ore sorting. Now, Grant's received a number of awards. He received the Minerals Engineering International Young Person of the Year at Comminution 18 in Cape Town. He's played a principal role in developing the energy curves, which was the topic of his CEEC medal winning paper. They're widely used by industry for benchmarking and really adopted by CEEC as a way to help inform and the industry on energy consumption. So welcome, Grant. Congratulations on your win.
Thank you.
Now, we think the paper you wrote was an important contribution to the industry and to the energy discussion because it's included the embedded or the embodied energy in grinding media and also the energy and ancillary equipment for equipment like HPGRs. So it tells a much better picture of the overall energy use of the different flow sheets, which helps inform people make better decisions. And for people who haven't read Grant's paper, I really commend they do because not only is it technically very good, it's really easy to read and very compelling.
Thank you.
Grant, could you sort of summarise the key messages out of that paper?
Yeah, so the paper really builds on a lot of the work that I've done in the past on the comminution energy curves. The energy curves were based on the electrical energy that the mills consume in the breakage of rock. This adds to that the embodied energy of the grinding media that's consumed in the grinding process. It's obviously to get that grinding media, steel grinding media, into the mill, it needed to have been mined. It needed to have been smelted, cast, and then transported to site before it's consumed. So there's a lot of energy that goes into that media before it was consumed in the mill. And then also the ancillary equipment around the grinding circuit. So the conveying of ore, transport of ore around the circuit, pumping of the slurry up to the cyclones. I really wanted to look wider than just the electrical energy of the mill or the mills and look at the additional energy consumers of the circuit. And I think it's really important to take those into account when designing
so sort of like the full life cycle.
Yeah. So not just the energy that's consumed by the mills, but consumed in delivering material, the balls to the mills, and also moving the rock around the circuit, because they can be vastly different for different circuit configurations and designs.
And they're quite significant too. The numbers in the paper showed that they really do change. Sometimes comparison between different options, they really do change the ranking.
Definitely. So we found that they can add between 30 and 50% on top of the electrical energy that the mills actually consume in electrical energy. So yeah, it's very significant.
So it could lead to some really false decisions if you don't include a bigger picture of the energy footprint.
Definitely. So I presented 2 different case studies in the paper. One looked at the trade-off between HPGR-based circuits and SAG milling-based circuits, and one that looked at what happened with a specific SAG mill over time as it went from autogenous grinding to semi-autogenous grinding to full pre-crush and higher bore loads in the SAG mill. And in both of those cases, including the embodied energy and including the ancillary energy changed the way you looked at that trade-off significantly. When you're talking about an HPGR, the amount of conveying that's required, you can double the HPGR energy to take into account the conveying. And with the ag mill to the barely autogenous mill at the end with full pre-crush, the consumption of media added a significant amount to that energy that wouldn't normally be taken into account, but I believe should be taken into account in those decision-making processes.
Mm. So if from the analysis there was just one concept or one learning you could take and you wish you could communicate easily to industry, what would be the one thing you'd say?
Well, it's a bit hard to pull it down to one because we looked at these two different concepts, the embodied energy and the ancillary. But I think if you took it down to one, it would be look wider than just the electrical energy that's consumed by the mill. That is one important part, but there's so much more to designing an energy efficient comminution circuit and operating in an energy efficient comminution circuit that should be taken into account. And I think this ancillary equipment, but and embodied energy in the grinding media are two major components of that puzzle that haven't really been looked into in any great depth previously, at least from the energy side of things. And we can reduce it. We can reduce the media consumption. There are well-known ways to reduce media consumption, and we can change the design of our circuits to reduce the amount of energy consumed in conveying and pumping. There's good solutions there.
Yeah, so I guess the first thing, the most important thing is just for people to know. If you've measured it, which, as you said, we weren't measuring it well before. If we measure it, we know it, recognise it, then we can think about ways to do something about it, or to choose the better option of the two, which maybe we didn't know was a better option until we measured on the larger scale, on the larger campus.
Yeah, definitely. And I think it was one of the reasons I wanted to pull it into the energy curves and add it into the group of energy curves is that it then provides a different way of showing it as well. I mean, we can write in a report that our ball mill consumes, 60 grams of media per kilowatt hour, and someone will nod along and go, okay, great. What does that mean? So being able to actually portray it in the energy curve format, where we take a well-known idea of cost curves and moving down cost curves into this way of visualizing it, allows you to communicate that to a much wider audience and gain better traction for those kind of ideas.
Yeah, so we might move to that, because you've been an instigator of the energy curves. I think I first saw you present quite some years ago at a conference. I thought that's what we need in the industry to help communicate the concepts. So you've been with it the whole time and driven it, and now you're adding to it, adding much more depth to it. So how do you think they're going to help the industry? And do you think, what more can we do to them to improve them? How do we help the adoption of them? And how can they help the industry, meet the challenges of reduced energy consumption?
So firstly, I've got to thank you for championing the energy curves. I remember in 2016 presenting to you in Vancouver, and the way you encouraged that work that I was doing and started getting a kind of movement behind it was really great. And we need more champions of that kind of stuff in the industry to push forward early career engineers and researchers in front of and get their research brought out. So I think it was really great for that to happen from you, and obviously through CEEC was the main kind of driving force behind that. But yeah, so the energy curves, the idea of it was really to bring together all of this data that we had of different operating sites, and to encourage people to reduce their energy. And the problem was there was all of this confidential information that was barreled up in this data that had been collected. And so we needed a way to present that in a way that that didn't display exactly where each one of the mines were and all of the confidential data within there. And that cost curve format of being able to present each mine as a bar on a chart and rank them from highest to lowest, and be able to show kind of movement from the top end. You're up in the top quartile, you can move down to the bottom quartile with these different changes. And this is a case study of another mine that has done that, and this is what we've seen elsewhere. It became really powerful, and I think made quite a difference in that time. So I'm hoping that it continues to gain traction, and I'm still a champion of kind of moving in that direction and presenting improvements in that way.
Yeah, so I guess we believe that it meets CEEC's objectives of communicating what's happening, so summarising the numbers, communicating them in a way they're useful and can communicate not just to engineers, but can communicate to the chief financial officer or the accountants or the CFO, the CEO. It can communicate that, but it can also give people a chance to identify good practice. Who has adopted a good practice, and what can we learn off that? So I guess their roles that CEEC is trying to help to play. Can I ask, like this work in the embodied and ancillary energy, is there more to go? I mean, what's next? Are there other things we should be including to improve that analysis, or are we getting pretty close now?
I think there's always ways to improve things. I think Zimi mentioned fragmentation from the mine, including the mine in the comminution process, which I think is really important. In terms of the energy curves, the drive to go to embodied and ancillary equipment came from presenting the energy curves in workshops and having conversations with the workshop attendees and them and discussing what they want to be able to show for their mine, and what they want to see going forward. And I think I've had a lot of other conversations about different things that should come in. I think one of the major ones, just it's kind of on the side, but is water. We've done this process of energy curves for comminution energy, but comminution doesn't just consume energy; it consumes water, and it also generates the fines that lock up the water in the tailing stands. So I think there should be some momentum towards pulling together this information into kind of a water curve or something like that. And I think there's some work in the background that's been pushing that forward. And I'd love to see that gain more traction in the industry.
Because I remember seeing some other work we did. We talk about core separation as one way to reduce, certainly clearly reduce comminution energy and water consumption. Some other work you did in the past just sort of pointed out that if it's particle by particle sorting and it's using compressed air, the embodied energy in the compressed air is quite high.
Yeah.
So I mean, that's just another example. Having a look at the big picture, but including water in the big picture certainly pushes us towards where we can separate dry and coarse. We should be doing that.
Yeah, and I think that's really important. And the paper you talked about, where we looked at the energy associated with the getting the air for the particle sorting. That started changing my perspective on kind of what on particle sorting and how that can be incorporated within a circuit, because obviously the energy required to load those particles per ton of rock rejected goes up as you go finer. So you liberate the material more, and you get more liberated gangue, but you consume more energy in the sorting process. So taking into account those additional things can actually lead you to a very different design point or optimal operation. Yeah.
Yeah, so they're driving us towards the bulk dry sorting technologies or bulk coarse sorting technologies like grade engineering or dense medium separation, gravity separation, or coarse flotation, where we don't need every individual particle with a pulse of air on it. We're looking at a more bulk separation.
Yeah, and while I've been at Zenco, I've been doing a lot of work in this area, and while I was at the JK, we looked at this progressive recovery that you should be recovering as material is liberated and gangue's liberated first at the coarsest stage. So I definitely think there's a lot of value that can be added with technologies like bulk ore sorting, reducing the amount of material going into your grinding circuit, increasing the grade. So you're using the energy and on the right material, and then grinding coarser. So reducing the work required in that comminution circuit to produce a coarser product that can be recovered through coarse particle flotation or other coarse separation technologies. And also, and in the middle there, so you've got the kind of reduce the material going to your comminution circuit, reduce the work required by a comminution circuit, but then in the middle, work on the efficiency of your comminution circuit. So there's a lot of really interesting technologies around dry crushing, VRM, vertical roller mills. There's the Vera Liberator. There's a lot of these different new technologies that are coming in that space that actually really complement the bulk ore sorting and the coarse particle flotation as well. So yeah, that's been one of the really exciting things about coming across to Zenco is not just looking at those things on a piece of paper and kind of looking at the technical benefits, but translating it, as Zimmy said, into the financial, right from the word go, and saying, where do we want to be in terms of NPV, and can we get there with these technologies, and what's the financial benefit of doing this?
And I guess also give me the opportunity to help, I guess, convince the client that there is a solution, there is an engineering solution to de-risk it. Zimmy talked about the risk that people want to avoid. So as a researcher, you talk about the potential. As an engineer, you have to talk about minimising the risk and how it's going to be designed to be robust and operable and maintainable. So that's really exciting transition to be able to have to do both.
Yeah, and I think one of the ways you can reduce the risk is by staging it. So do staged implementation, and that's one of the things that all of the projects that I'm kind of working on with these technologies start off with a pilot style, where a pilot is actually full scale, but a smaller full scale. So it allows you to test the equipment, but not waste capital on it. It then becomes the full scale implementation, just more of those or at a greater level. So yeah, we work a lot on that risk side of things. For instance, bulk ore sorting. There's a lot of risk associated with what is the heterogeneity of the ore body? How variable is the grade that's coming out of the mine? And we've developed a lot of techniques to be able to assess that and to be able to evaluate that in situ. So measuring through drill cores what that variability is going to be down down the conveyor belt when the mine's operating. All of those kind of things, and different modelling techniques that we've developed, looking at putting coarse particle flotation within a full value chain and running your mine plans through that and working out what the economics are and where the optimal operation is. So I think all of those are really important in de-risking these new technologies. But look, a lot of them are ready.
So what do you? So yeah, that's right. You're familiar with them. You've done research on them. They're doing engineering with them. What do you think is, let's say, in 10 years' time? Now I know every ore body is different, but a sort of, if there is such a generic ore body, such a thing, what do you see as the processing plan of the future for energy efficiency and water efficiency? What sort of components is it going to have?
So I've been doing a bit of work on this with a few clients actually. So I think for copper, I've got the best examples I can give for copper. I mean, gold's going to have different commodities are going to have different views. But if I look at copper, I think the mining is going to become. I think the mining is going to become less selective, and the selectivity is going to come through bulk ore sorting or different separation techniques at that coarse size. So it's going to be less about grade control and digging to polygons and all of those kinds of things, and more about get it out as quick as possible for as low cost as possible, and then separate it. So I think that's one side, and I think then we can get a higher grade feed to our processing plant to make that more economic. And when we get a higher grade feed to our processing plant, we're pushing more value through that bottleneck, and that generates more NPV. I think in terms of the comminution technologies, I don't think SAG and ball milling are the enemy, as a lot of people think that they are. I think there are effective ways that are going to be found to operate them well. For instance, I've been recently looking at some really old work in the 1950s and some even earlier work in the 1920s that looked at operating mills at low filling and low speed to produce dramatically improved energy efficiencies. And that's something that hasn't been looked at as much recently. So I think there's different ways that we can operate them. Then there's going to be totally different equipment. And there's a number of really exciting equipment, specifically around dry comminution. And as long as that doesn't increase the classification energy, so another ancillary thing, but dry classification can use a lot of energy. As long as it doesn't increase that to a high level that currently does, then we can implement those technologies. And then I think coarse particle flotation is really a key. And there's a lot of companies developing new equipment at the moment to look at coarse particle flotation. Obviously, there's the HydroFloat, which we put in at Cadia, and that's a great success down there. And there's so many other applications currently being looked at and being developed. So that coarse separation, the pre-concentration, whatever you want to call it, moving through to efficient comminution, moving through to coarse particle flotation, creating tails that can be dewatered very simply and cheaply, and stacked, stable, produce a stable stack, dry stack. We can reduce energy by 50%. We can reduce water by 50%. We can reduce tailings by 50%, combining with some other things. But we've done projects where we've looked at that. So substantial. And I think we can do it now. So that's what I'm looking forward to.
So do you think we're communicating that well enough? I mean, if we're going to get there in 10 years' time, is that well enough communicated? And if not, what can we do better? What can CEEC do better, even, and your company?
I think one of the things that is lacking from the communication side of things, and it might sound funny coming from me and talking about energy and those kinds of things, is that we focus too much on energy sometimes as engineers. And sometimes we need to take that step back and say, what are the financial consequences of this? And I've been amazed since starting at Zenko and being able to do those calculations and focus on the financial, on the NPV, on the NPV on capital ratios, and defining those things that we can really drive to an energy efficient solution without necessarily having energy as the driving point. And I think that's really important. The comminution circuit is key to this. Obviously, it is the highest capital component. It should be the bottleneck, and therefore, if we can drive more value through that bottleneck, we're going to create not only a more economic mine, but we're also going to result in a more energy efficient process as well. And all of the work that I've done kind of points in that direction. So yeah, I think that's really important.
Yeah. So the big changes you think the industry needs to be adopting in the next 10 years? When we talk energy, obviously, and economics, but there's water as well, there's social governance. What are the technologies or combination of technologies and the changes we need to be able to?
Yeah, so I think we need to, I kind of touched on it earlier, the comminution circuit creates fines. The fines are what consumes the energy. The fines are what needs to be placed as a tailings. The fines are the ones that consume the water in the tailings, so that can't be recycled, so you have a lower recycling rate. So I think the biggest challenge from my perspective is reducing the amount of fines that we produce. That to me focuses all three of those things together. It brings in energy, water, and tailings together, which are, I think, the three major technical elements that we need to be solving. So reducing the amount of fines that we generate by pre-concentrating and producing a coarse waste, by being energy efficient in our comminution and not generating those fines in the comminution process, so using classification screens rather than cyclones and those kinds of things, and not over grinding material, and then separating as coarse as possible. Those things, all of them, reduce the amount of fines that we generate, and that is key to energy, water, and tailings, I think.
Well, thanks, Grant. I like what you're saying, and we've got a lot of work in front of us as operators, as engineers, as researchers, I guess industry supporters like CEEC. We've all got a lot of work in front of us to get there, but I think you're painting a picture that there is a path we can take.
Yeah.
It's not going to be easy, but we can take it. All those groups need to really focus on the same things. So thanks for your time, Grant. Congratulations once again on your CEEC medal win, and all the best wishes for your ongoing success and innovation success in the industry.
Thank you very much.
Grant.
Thanks, Jay. Cheers.